first speaker, Dr. Nozimjon Tuygunov from University of Hong Kong, Faculty of Dentistry. Please.
Yeah. Well, hello everyone. This is Nozimjon Tuygunov. I am Master of Dental Science from University of Malaya, and I've been working in the University of Hong Kong in HKU. And today I'll be presenting my research entitled Fabrication of Novel Nano-Sized Glass Ionomer Cement Formulation with Enhanced Bioactivity Properties. Well, here's the outline of my presentation. Well, let's start with introduction. So as we know that conventional glass ionomer cements are acid-based cements with widespread usage. It presents a better preventive effect on caries than other restorations on primary and permanent dentitions. It has some advantages and disadvantages as well. Advantages like chemical bond to enamel and dentine, fluoride ion release and its accumulation, reduced microleakage on dentine, biocompatibility, anti-carcinogenic action, and cost efficiency. However, it presents some disadvantages, which are high wear rate, poor mechanical strength, less aesthetic, initial setting time to water loss and uptake. Well, if we will be talking about the chemical composition of our conventional GICs, it consists of about 80% of silicon oxide and aluminum oxide and 20% of additional chemical elements, which might be fluoride-containing agent, sodium, and heavy metals like lanthanum and other heavy metals. Well, if we'll be talking generally about its particle size, basically glass ionomer cements are not divided by its particle size. However, the particle size of our material can be varied from 5 up to 20 micrometers. So here on our right hand on the table, we can see the different particle size of the different commercially available conventional glass ionomer cements. And tetracalcium phosphate, this is one of the type of calcium phosphate which calcium and phosphate ratio greater than hydroxyapatite, and which value is 2. Studies have shown that TTCP can promote osteogenesis, exhibit dentin breach, and can be used for dentin hypersensitivity, has high biocompatibility as a pulp capping agent, stable in bacterial medium, and can be used for root canal perforation. Additionally, it increases remineralization properties when it's used in chewing gums or in toothpaste. Hydroxyapatite or HAP, this is also one of the type of calcium phosphate, which calcium and phosphate ratio is 1 to 1.67. Well, studies have shown that HAP holds significance in medical and dental domains such as osteoporosis treatment, alveolar bone repair, and prevention of dental caries. In toothpastes, it is also shown a good properties when it was used as a repairing agent. Additionally, it enhances bioactivity properties of the material used in restorative dentistry, and some studies have shown that HAP increases mechanical strength of our material. Well, nanotechnology in dentistry so based on the ISO standard, nanotechnologies are the particles, the materials which dimension of the particle is from 1 up to 100 nanometers. So limitations of the nanotechnologies are follows, which are biological limitation, chemical, mechanical, social limitation, ethical, or there might be economical limitations as well. Well, statement of the problem. Well, as we know that in conventional glass ionomer cements, the bonding between the conventional GIC and tooth is weak. Why it is weak? Because a stronger chemical bond could be achieved by fabricating GIC with true bioactive properties. For example, formation of hepatite interlayer by enhancing fluoride calcium or phosphate ion release. For conventional GIC, it is considered difficult to form such apatite layer because the release of polyacrylic acid from the GIC lowers the pH and inhibit the formation of apatite. Thus, it's necessary to develop bioactive GIC that can increase calcium and phosphate ion release. Well, basically, the aim of the study was to fabricate nano-sized GIC powder formulation modified with TTCP and HAP and investigate its physical, chemical, and mechanical properties. Well, we divided the objectives into two. First was to synthesize nano-sized GIC powder and assess its chemical and physical properties. In our next objective, we modified our nano-sized GIC powder and with HAP and TTCP and investigated its chemical, physical, mechanical properties, and we compared it with commercially available conventional GIC formulation. Well, hypothesis of our research was to fabricate the nano-sized GIC powder will result in distinct elemental composition, phase analysis, and particle size distribution compared to commercially available conventional GIC formulation. The modified nano-sized GIC powder will result in significant improvement ion release, mechanical strength properties, and will shift the pH towards more neutral environment. So here is materials and methods. Well, based on our first objective, we fabricated nano-sized GIC powder using sample melt quenching, and two-step ball milling procedure has been proceeded to decrease the particle size of our material. Then chemical analysis such as EDX, XRD, and FTIR has been employed. As a physical analysis, we use particle size analysis and scanning electronic microscope to confirm the presence of nanoparticles in our material. Well, the next is, well, based on our objective 2, we modified our GIC powder with calcium phosphate and investigated its chemical properties, which is EDX, XRD, and FTIR. Then we employed SEM, initial setting time, pH, and ion releases such as calcium, fluoride, and phosphate. As a mechanical strength analysis, we used compressive strength analysis. So here is how we used to fabricate our material. So silicon oxide, aluminum oxide, calcium fluoride, P2O5, and calcium oxide has been mixed, and we place it in an electric furnace, and we melted up to 1,250 degrees, and we hold for 2 hours. Then we rapidly quenched our material into cold water. Then, in order to decrease the particle size up to nano, we used ball milling procedure. In the first step of the ball milling procedure, we used the sieve with the mesh size of 106 millimeters. Then we used we set up our machine for 300 RPM for 2 hours. And we mixed 1 gram of our powder with 10 grams of zirconium balls. And the jar capacity was 50 ml. After that, we proceed with the second step of our ball milling procedure, which is where we use zirconium balls with the diameter of 0.5 millimeters, and we grind it for 300 RPM for 2 hours. Then we used to analyze its chemical properties, which is, I have already mentioned, EDX, XRD, and FTIR. For physical analysis, I proceed with PSA and SEM to double confirm the presence of the nanoparticles in my material. Then I modified my fabricated glass ionomer cement with calcium phosphates, which is TTCP and HAP. To mix the chemical compounds, I used multi-purpose grinder for 3 minutes to apply consistently the force and time. As you can see here in the table, we can see the groups we have. We had in total 7 groups with different compositions of TTCP and HAP. And group A, we used as a conventional glass ionomer cement. We used as a control. After modification of our material with calcium phosphates, we evaluated its chemical properties, then physical properties, then mechanical properties. Well, statistical analysis has been evaluated using one-way ANOVA with two key HSD post-hoc analysis, and data was found normally distributed. Here we can see the results of my study where we fabricated of our nano-sized GIC powder. Here we can see the particle size analysis after, here on your left hand, we can see the particle size analysis before proceeding with ball milling procedure. Here on our right hand, we can see the particle size analysis after first step of ball milling process, which revealed to 224 nanometers. However, here, after first step of ball milling process, as you can see, the particles has been distributed not homogeneously. Right? Then we proceed with the second step of our ball milling process, and as a result, we can see that we evaluated different batches, and from different batches, we got the mean 95 nanometers of our particles. Well, here is the results of our commercially available glass ionomer cement, which revealed to 769 nanometers with 100% of homogeneity. Well, based on the ISO standard, we cannot rely on only one PSA analysis and say that this is nano-sized. We have to double do additional tests like microscopic analysis. So we proceed with FESM analysis. So FESM analysis revealed 80 nanometers of our particles. On your right hand, it can be seen. On your left hand, we can see the size of the particles of the commercially available glass ionomer cement. Here we can see the chemical composition of our commercially available product and our synthesized glass ionomer cement. Here, I think the main difference we had, and it might be one of the limitation of our study, that in our fabricated glass ionomer cement, there are no heavy metals, which makes our material less radio opaque. So in commercially available product, we can see that there is strontium ion, strontium heavy metal has been incorporated as a to increase the radio opacity of our material. Then here we can see XRD analysis of our material and commercially available GIC. Here, as you can see, so based on the literature, so there is only silicon oxide can be evaluated based on the peaks we had in our graph. So here we can see FTIR analysis of commercially available GIC and fabricated GIC. And here as well, we can see no significant difference between commercially available product and fabricated GIC. Now we can see the XRD EDX analysis of different groups. This is based on our objective 2. As you can see, group C, which was consisting of 10% of TTCP and 0% of HAP, and group G, which consists of 0% TTCP and 10% of HAP. Here there was higher, as you can see in group C, there was higher calcium and phosphate ratio. It revealed to 2.1. However, in group G, where it was consisting of HAP, it was 1.7. So it can be easily understood that based on the chemical composition of TTCP, calcium and phosphates ratio, it is 2, and HAP's calcium and phosphate ratio is 1.67. So that's how we can prove the presence of calcium and phosphate based on our EDX analysis. Here as well, in XRD analysis, we can confirm the presence of HAP and TTCP in our different groups. FTIR analysis also provided the comprehensive analysis of different materials. So peaks here, they show the presence of phosphate ion in our material. So here we can see the analysis of the powder of our material. These here are the different materials we can see under the SEM analysis, and we proceed with porosity analysis using IMAGE software. As you can see that group C, which consists of 10% of TTCP, the porosity area was 50%. However, group G the porosity area was 41%. So porosity can be easily like connected with the compressive strength analysis of our material. When porosity is higher, the mechanical strength of our material has been decreasing rapidly. Here we can see the porosity, the results of the porosity in different groups as well. So here we can see the initial setting time analysis. Well, based on the ISO standard, the initial setting time of our material should be from 90 seconds up to 480 seconds. We can see that group B and group F and G, they are among the ISO standard. However, group C, D, and E, it is a bit higher than ISO standard. Here we can see the statistical difference between our different groups. Here we can see the pH analysis of our different groups. We can see from here that the modification of GIC showed a significant difference and shift in initial pH from acidic to more neutral. The most acidifying material was commercially available product, which had the lowest pH. So what pH gives us? It makes our material less, it can make our material less, like easier to cause secondary carries. Fluoride ion release. Well, if we will be comparing all the commercially available product and all our groups, there was I would say there was no significant difference between the groups in different time points. For all the samples investigated, the quantity of fluoride ion released was the highest after the first day, followed by progressive decreasing in release up to 28th day. Well, here we can see the calcium release, and here we can see the phosphate release. As you can see, the calcium and phosphate ion release has been increased rapidly when we incorporated calcium phosphates, which is TTCP and HAP. Here we can see the mechanical strength analysis of our different groups. So based on the ISO standard, in order to use as a restorative material, the compressive strength analysis should be higher than 100 MPa. However, in order to be used as a liner, the compressive strength analysis should be no less than 50 MPa. So as you can see from here, from the graph, we can say that all material can be utilized as a liner. However, only group F, G, and B, they can be utilized as a restorative material. Here we can see the statistical difference between different groups in the compressive strength analysis. Here we can see how the porosity can be connected with the compressive strength analysis. As you can see, when the porosity is 41%, the compressive strength was 112 MPa in group G. However, when porosity has been increased up to 50%, the compressive strength has been decreased significantly up to 77 MPa, which is group C, consisting of 10% of TTCP. Here we can say that HAP has been increased. HAP was used as a material to increase its mechanical strength analysis. Well, as a conclusion, we can say that nano-sized GIC powder shows variation in chemical composition, confirming the amorphous phase in both fabricated and commercially available products. TTCP and HAP's incorporation in fabricated nano-sized GIC powder prolongs initial setting time. TTCP and HAP integration boosts calcium and phosphate ion release, shifting the pH of our material to more neutral environment. HAP inclusion enhances compressive strength, while TTCP reduces it. All are effective as a liner material, but only two groups, which are E and F are suitable for restoration. Well, here are the limitations. The analyzing of porosity in 2 dimensions may limit understanding of volumetric characteristic and spatial distribution within the cement matrix. Using a single sample size might not capture the full variability of cement's characteristics. Well, future recommendation for porosity assessment, it is recommended to utilize advanced techniques like mercury porosimetry and helium pinometry, offering insights into 3D distribution and structural integrity. Conduct bonding tests to evaluate the effectiveness of fabricated nano-GIC powder modified with TTCP and HAP, aiding in understanding adhesive capability for diverse application. And of course, it is recommended to evaluate the materials bioactivity with SBF. So I think that's all from my side. If there are any questions, please feel free to ask me.
Nozim, thank you so much for your research, for your presentation, and also for Sam for his contribution in this conference.
Yeah, thank you, Prof. Thank you too. Thank you so much. Thank you for inviting me.
Welcome.
Can I just say, Nozim, it was a very nice presentation and you did a great job. And thank you again, Marian, for giving a place for Nozim. And so he's up and coming excellent researcher. And thank you very much. Thank you.
Thank you, Prof. Thank you. Thank you so much.
Really, it's an excellent research.